Hi everyone. Today I'm going to go over differential calculus 2. So the first was all looking at kind of the basics of differentiation and just getting used to different operations and this sort of thing. Now the next thing to look at is basically the second derivative. Okay, so if I have a function f of x and I get the derivative, this is the slope. But what happens if I take the second derivative? So this is just when you do ddx of f of x. So you just differentiate it twice. What do you get? You basically get the rate of change of slope. Okay? So you just get rate of change of slope, and that'll come in handy in a while. Okay? But for now, that's all you need to know. So, a couple of examples. If f of x is equal to 5x squared plus 2x minus 6, first of all, what's f prime of x? So f prime of x is, again, using the power rule. So remember the power rule. If you do ddx of ax to the n, is just an x to the n minus 1. And if you differentiate a constant, you just get 0. So, sorry, that makes that look like a 3. So you bring the 2 down, you get 10, you minus 1 off the power, so I end up with x. Differentiate 2x, I just get plus 2. Differentiate minus 6, I get 0. Now if I differentiate it again, so differentiate this thing now, I'm simply going to be left with 10. Okay, so the second derivative of this function is just 10. Okay, so not too bad. So now I'm going to be looking at just increasing and decreasing functions. They can ask you for what values is this increasing and decreasing. So let's say I have x squared. For what values is x squared increasing and decreasing? Well, you can plot this out and it'll be fairly obvious. So decreasing, what we mean by decreasing is if x increases, does the value of the function increase or decrease? So if x increases, do we go up or down? So here, if x increases, we go down. And therefore this side is decreasing. But if we increase up here, x is increasing. And therefore it is decreasing over here and increasing here. Okay, so fairly obvious. But we can also use derivatives to figure this out. So if I take f prime of x, it's just going to be 2x. So again, the derivative of x squared is just 2x. So now, if I ask you, when is this decreasing? It's decreasing if f prime of x is less than 0, and it's increasing if f prime of x is greater than 0. So remember, this is just slope. So what I'm saying is, I'm saying that if the slope is negative, so the slope is negative on the left side over here, therefore it's decreasing. The slope is positive on the right hand side here, and therefore it's increasing. Okay? So that's all I'm saying there. So that's another way of doing it. So if I ask you, okay, so for decreasing, I need f prime of x to be less than 0. So I need 2x to be less than 0. And therefore, x less than 0 means you're decreasing, which is true. So remember, if you're left, so if x is less than 0, then you're decreasing. And then if I say, oh, okay, well, I want it to be increasing, so I want 2x to be greater than 0. That means that x has to be greater than 0. and therefore anything up over here is going to be increasing. Okay, so if they ask you, is it increasing or decreasing, you just take the derivative and then you go from there. Okay, that's all. Nothing more needs to be said about those. Okay, now, stationary points. Stationary points are basically when the slope is 0. Okay, so it's called a stationary point because the function isn't increasing or decreasing at that point. So if we have some cubic like this, it has two stationary points here and here. So a stationary point basically means that the slope f prime of x, which is again just the slope, is equal to 0. So if I look at the tangent to the graph at these points, I'll see that the slope is simply equal to 0. Okay? So very important distinction. Now, this point, so these points are both stationary points. The green is called a local max. And this one is called a local min. So a local maximum and a local minimum. Now you might say, well, hold on, that doesn't make any sense. Why is it called local? What does local mean? Local means that if you only look a small bit, so let's say we only look a small bit left and right, it's the maximum point. That's what it means by local. So like locally, if you just look kind of around the point, is it a maximum? Yes, then it's a local maximum. Now, is it a maximum in general? No. Why? Because this point of the graph gets higher than this. So if I draw a line over, there's points of the graph that go higher than the local max. That's why it's called local. It's not a global max. It's not a maximum everywhere. It's just a local maximum. If you look around the point, then it's a maximum. Okay. It's also these stationary points are also called turning points. Why? Because if I look at the slope is positive, 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 and then it changes to negative. And then it goes back to being positive. So if you go through a stationary point, or a local max or a local min like this, typically always, if it's a local max or a local min, it will always be that the slope changes sign. So it's either positive and then negative, or it's negative and then positive. Okay. For a local maximum, okay, so basically for these stationary points, you get that f prime of x equals 0. So if I plug in the x value that these have, I will find that both those will give me a value of 0. Now, the difference is that for this one, f prime prime of x is less than 0, and f prime prime of x for this one is greater than 0. Why? Remember what f prime prime is. F prime prime is the rate of change of slope. So f prime prime is how is the slope changing. If we look from this side to here, what's happening to the slope? It's going from positive to negative, which means the rate of change of slope is negative, and therefore it's less than 0. Okay? So basically, I'll do a few examples, but for this one then, it's just you start negative and your slope is always getting more and more and more. It's getting less steep, less steep. So this could be -5 of a slope, this could be -4, -3, -2, -1, 0, 1, 2, 3, 4, on and on. Okay, so that's the main thing to note about this. Okay, that you have stuff like this. All right. Okay, So that's that. So that's how you'll tell if it's a local max or a local minimum. I'll also do the point of inflection while I'm here. There will be a point somewhere along here where f prime prime of x equals 0. This is called a point of inflection. So they can ask you, where is the point of inflection? You will get f prime prime, you will equal to 0, you will solve for x, and you know the x value, you plug that x value back into f of x to see what the y value is, and then you're finished. Okay? All right. So now, let's do some cubic function. Okay? So, for a cubic function, let's pick something like this. So f of x, x cubed minus 7x squared plus 3x plus 10. Okay? So, actually, no, sorry. I'm going to redo this. Okay, I probably should have had this prepared, but oh well. Yeah, if I do this, I get x squared plus x minus 2. So x cubed plus x squared minus 4x squared minus 2x minus 5x, so minus 7x plus 10. Okay, so if I take this as being my cubic, the only reason, if you're wondering why I did this, basically these are the roots. So the roots are 1, minus 2, and 5. So it just helps me to be able to draw it. So the roots are going to be 1, 5, and minus 2. Remember, this is greater than 0, which means the right arm points up, like so. So it will look something like this. And then it will hit somewhere up here, where this is 10, because of the y-intercept. And it will go down forever, like that. So first of all, if I say, okay, well, where's the local maximum? It's obviously here. The local minimum is here. And the point of inflection is probably somewhere along here. Okay? So first of all, let's figure out where is my point of inflection. Okay? So your point of inflection is f prime prime equals 0. So first of all, f of x is going to be x cubed minus 4x squared minus 7x plus 10. So first of all, the first derivative is going to be bring down the 3, minus 1 half the power, bring down the 2, minus 1 half the power, and then this is just minus 7. So this is f prime. F prime prime now, again, take the derivative again, so it becomes 6x minus 8. Okay? So now, let's get the point of inflection. So the point of inflection, I need f prime prime of x to equal 0, which means I need 6x minus 8 to equal 0. So 6x equals 8, so x equals 8 over 6, which is 4 over 3. Okay? So now, to figure out what the y value is, I need to calculate f of 4 over 3. Okay? So that's going to be 64 over 27 minus 64 over 9 minus 28 over 3 plus 10. all divided by 27. Okay, this is going to be a right pain to do. Minus 128 minus that times 9 is going to be 252 plus 270. That's going to be, so this part here is plus 18, so it's minus 110 over 27. 27 doesn't go in, does 9 go in? Nope. Does 3 go in? No. So it's just that. So the point of inflection is equal to 4 over 3 minus 110 over 27. So that's the point of inflection. Okay? So this point here is equal to 4 over 3 minus, so it's going to be 4 over 3 minus 110 over 27. So that's the point of inflection. Now, if they ask you, okay, what's the coordinates of the minimum and maximum? So again, local min. Why? Because this branch here is lower, therefore it's only local. And the same thing up here. This branch is higher, and therefore it's only a local maximum. So if they ask you for the local max and the local min, you'll say, okay, I need f prime of x equals 0. F prime, we calculated there a while ago. That's 3x squared minus 8x minus 7. Oh, sorry guys. Plus minus 7. Okay. So if I solve this using the minus b formula, I don't think this factorizes, unfortunately. So if I use the minus b formula, I'm going to get x equals 8 plus or minus the square root of 64 plus 84 all over 6, which is 8 plus or minus the square root of 148 all over 6. Okay? Blah, blah, blah. So plug that into your calculator, plug it back into f of x the same way that I did up here, and that'll be your local maximum and local minimum. Now, if I ask you, which one is going to be the local max and which is the local min? So this, remember, it's 8 over 6 plus minus the square root 148 over 6. So which do you think it is? If I add it, will I get the minimum? Or if I minus it, will I get the minimum? So where's the minimum? Where's the maximum? This is the x value. So remember, go back to your graph. If the right arm points upwards on a cubic like this, it means that the minimum is further right than the maximum. So the maximum has a smaller x value. And therefore this is going to be the minus, and this is the plus. So if I minus it, down here, I will get the local max x value, and if I add it, I'll get the local minimum x value. Okay? So hopefully that's okay. So that's a question that covers everything that you could be asked in terms of points of inflection. Okay? And again, if they asked you, where is the function increasing? It's increasing here. It's also increasing here. And it's decreasing in here. Okay? All right. So now it's maximum and minimum problems. So it could say something like this. You have a box like this. You're going to cut cardboard out of it to make a box. Like so. This is x. This is also x. Sorry, I should have drawn these better. But all of these are just x's, okay? this length here is 30, and this length here is also 30. And it says, what they're doing is they're going to fold this left-hand side up, they're going to fold this up, and they're going to fold this up. And basically what they're asking is they're saying, what dimensions will yield a box of maximum volume? Well, first of all, we need to figure out what the volume is. So first of all, what's the height? So if I were to put the box together like this, what would I have? I'd have, well, the height is x, grand. The length, this is going to be 30 minus 2x down here. So the whole length is 30. You have x here and x here. So what's left here? 30 minus 2x. Okay? And the same thing on the other side. So again, this is x, this is x. This is 30, so it's just 30 minus x. Okay? Sorry, 2x. So the volume is going to be 30 minus 2x squared times x, which in this case, if you do this out, you are going to get 4x cubed minus 120x squared plus 900x, like that. And then they might say, okay, well, what's going to be the maximum or the minimum of this, what value of x will lead the maximum? So they want to know what's the maximum volume you can have. So if I have a sheet of, say, wrapping paper and I want to have the most amount of wrapping, I'm cutting out these bits. So I'm just left with the bits. What value should x be to give me a maximum value? And it's not too bad. I just want to know, if I plot this out, it's going to look like this. Now this isn't important, I'm only doing this because I think it's just handy to see 15. So it looked like this. Okay? Now, if I asked you, what's the smallest value that x can be and what's the biggest value? Whenever you do these questions, you always have to look at the dimensions. What can lengths not be? They cannot be negative. So first of all, I have that x has to be greater than 0. So sorry, I should have said this is 15, by the way, and that's 0. So x has to be greater than 0, but also 30 has to be greater than 2x. Why? Because this has to be greater than 0. So I have that 15 has to be greater than x. So whatever answer you get, it's going to be some way within these two values. Okay? So what I want to know, okay, where is the local max in these values? So you get d dx. So if I get d dx of 4x cubed minus 120x squared plus 900x, I get 12x squared minus 240x plus 900. And what value do I want this to be? I want it to be 0. Why? Because at a maximum, the slope is equal to 0. Why is the slope equal to 0 at a maximum? Because if you think about it, again, the slope is going positive, 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 so it's going up. If the slope is positive, it's going up. So it's going up and 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 up. And it's only when it stops going up, or when the slope is 0 and it becomes negative, that's when it starts to come down. So I want to know, when is this thing equal to 0? And I solve this equation. So I think I can divide by 12. Yes, I can. So if I divide by 12, I get x squared minus 20x. I feel like it's plus 75. I think, yeah, it's 75 equals 0. So now this should factorize into minus 5 and minus 15. So x equals 5 or x equals 15. So those are your two options. Now, which one is it? Remember, we said that x has to be less than 15 and it has to be greater than 0. There's only one answer here that fits that, and that's x equals 5. So the answer is, if I want to maximize the volume, I want x to be equal to 5 centimeters. Okay? If I plug 5 into the volume, what am I left with? I'm left with 4 times 5 cubed minus 120 times 5 squared plus 900 times 5. 5 cubed is 600 minus 3000 plus 4500. So the maximum volume is going to be 2000. Okay. Did I mess this up? Yeah, that's 500. Sorry, it's 125. So 125 times 4 is 500, not that. So it's just 2000 centimeters cubed. So that's the maximum volume that you can have. Okay? All right. So now I'm going to do one hard question, maybe two. I'll see. What time did I start at? Okay, so we've been going for a while. And it's definitely worthwhile to do one or two more, and then it's rates of change, and then that's it. Yeah, the very last thing that I want to do is rates of change. Okay. So here, it says a sector of a circle. So this is theta. This is r. It says show that theta equals 200 over r squared. So the area is equal to 100. So your area is equal to 100. The area of a sector of a circle, remember, it's pi r squared times how much of the circle do you have? You have theta over 2 pi. Okay? So it's theta r squared over 2 is equal to 100. So solving for theta, I get theta is going to be 200 over r squared. Okay? So that's it. It says explain why r has to be greater than root 100 over pi. So to do these, you always have to say what's the maximum you can be. So first of all, r obviously has to be greater than 0. Of course it does. But do we have any constraints on theta? Yes. Theta has to be greater than 0, but it also has to be less than 2 pi. Because they told us that we have a sector of a circle, which basically means that we don't have a full circle, and therefore it's less than 2 pi. Okay? So if theta is less than 2 pi, this means that 200 over r squared has to be less than 2 pi. So if I multiply both sides by r squared and divide by 2, I get 100 has to be less than pi r squared. Or 100 over pi has to be less than r squared. Square root both sides has to be less than r. So r has to be greater than this. Okay? The next thing that they ask you to do is they say, show that the perimeter of the sector is given by this. So basically just find the perimeter. So what's the perimeter? The perimeter is the length of the outside. So it's r plus this length plus this length. So the perimeter P is going to be r plus the circumference. So the circumference, remember, is 2 pi r multiplied by theta over 2 pi. Remember, this is how much of the circle do I have. So we're seeing it pop up twice. Okay? And also remember, we have that theta is equal to 200 over r squared. So we get that this is equal to 2r plus, it's going to be theta r. So it's 2r plus theta r, where theta is 200 over r squared, so it's 200 r over r squared, so it's 2r plus 200 over r. So that's the perimeter. And then it says, find the value of r that minimizes the perimeter. So again, if you want to maximize or minimize anything, you always differentiate. That's one of the biggest things. If you're sitting there and it says, what is the max min? The second you hear max min, it should just be differentiate. That's what you're kind of going for, okay? Like, if you could ring me during the exam and you say, hey, Adam, you know, you read out the question, you say, oh, it's asked me to find the maximum. Instantly, I would be like, differentiate. That's the very first thing we think about. You just say differentiate, okay? So if I differentiate and get dp dr, 2r differentiated with respect to r is just 2. Remember, (200 over r is the same thing as 200 r to the minus 1. This is another thing that's very important. You have to be strong with your indices or else you're going to find this quite hard, okay? All right. So now that we have this, I can differentiate this. It's going to be minus r to the minus 2. And remember, I want this to be equal to 0. Okay, so I want 2 to equal 200 r to the minus 2, which is just 200 over r squared. Okay, so I can cross multiply and say 2r squared equals 200, r squared equals 100, and therefore r has to equal 10 if you just take square roots on both sides. So it's r equals 10 centimeters would be the answer. Okay. All right, so hopefully that's okay. I want to do another one. What's another difficult one? Yeah, I think I can see something like this coming up. So it basically says you have a computer manufacturer determines that in order to sell X units of new computers, the price per unit in euros must be this. So P of X needs to be 1,200 minus X. So if they want to sell 10, you have to plug 10 in here. If they want to sell 20, you plug in 20 in here, and so on and so on. Okay? And they say the manufacturer also determines that total cost of producing X units is given by this. So C of X plus 20X. So this is like your fixed costs, and this is your variable costs. Okay? Okay, so it says find R of X, the total revenue. So the revenue is just basically, so the revenue is just saying, okay, well, how much money do you actually make? So let's say you sell X computers, how much do you make? Well, that's how much you're selling them for. And if you sell X of them, then you take in that amount of money. So it's just 1,200X minus X squared. So that's how much money you take in. So hopefully that makes sense. So remember, this is per computer. So if I sell X of them, then that's how much money I actually make. Okay? And then it says, figure out what the profit is. So the profit, so sorry, I might use capital P here. So that's small p. So capital P is going to be revenue minus the cost. So this is the cost of producing X of them. So it's not the cost per one, it's the cost of all of them. Okay, so it's just minus 3500 plus 20X. So I get that it's going to be 1,180X minus X squared minus 3,500. That's my profit. Okay, and then they say, how many units must the company produce and sell in order to maximize the profit? So if they want to maximize the profit, what does X have to be? So again, maximize, differentiate. If I differentiate this, I get 1180 minus 2x. And again, you want minimum maximums, so you equal it to 0. So I simply get that x is going to be 590. Okay? And if they ask you what the maximum profit is, you just get P of 590. And then you just plug it back up into this equation up here, okay? And you see what that is. I'm not bothered with doing 590 squared in my head. Okay. And that's it. All right. So hopefully that's all okay. I do think this is quite difficult. But once you do a few of them, hopefully it won't be too bad. Okay. Now, rates of change. This is by far the hardest bit of things to do. Okay. So a rate of change is basically, they will give you some sort of rate of change and they will ask you for another. So they might want to know what's dy dt, and they might give you dy dx. And then you'll have to be confident enough to basically figure this out, that these two things basically cancel and I'm left with the same thing. Okay, so this is the hardest part about the rate of change. It's clocking what is it I actually want to do. So basically the way the question goes is they will ask you for a certain rate of change. You will write this. They will give you another rate of change, which is this. And you will be able to figure out the other rate of change. Okay, so it'll become much more obvious as I'm doing it. Okay, so basically a question here, it says the area of a healing wound is given by the area is equal to pi r squared. Okay, it says if the radius length is decreasing at a rate of this. So what have they given me? They've said if the radius is decreasing at a rate. So what does that mean? That means dr dt equals what? It's decreasing, so it's minus at 0.5 millimeters per day. At 0.5 millimeters per day. Okay, so here they've given me this. Okay, and then they say, how fast is the area decreasing? So what are they asking for? They're asking, what is dA dt? Okay. And now what you do is you say, okay, well, this is what I'm looking for. This is what I have. What do I need to multiply this by to be left with dA dt? So the dt and dt, they can stay. That's fine. I need to get rid of the dr. So I'm going to divide it by dr. And I need to end up with a dA, so I put dA on top. Okay? So remember, this is what I'm looking for. I've been given this, and this is something I can figure out. So what's dA dr? dA dr, if I differentiate this, I get 2 pi r. So dA dt is equal to minus 0.5 times 2 pi r, which is equal to minus pi r. And it says, what is, how fast is the area decreasing at the instant when the radius is 10? So when r equals 10, how fast is it? Minus 10 pi, be very careful, millimeters squared per day. So be careful with the units. Remember, it's area per time, so it's area per time. Okay? All right, so hopefully that's okay. I'll do another one or two of them. I think I'll do this one here because I think it's quite hard. Okay, so basically what we have is a cone is like this. It says is placed that is standing on its apex, so it looks like this. Water is flowing at a rate into the cone. So water is flowing into the cone at a steady rate of 1 meter cubed per minute. 1 meter cubed per minute. What's that? That's dV dt. So the volume is increasing at a rate of 1. Okay, so this is the hard part. You need to look at that and say, okay, if they tell you water is flowing into the cone at a steady rate of, so again, they said rate. If they say rate, it's basically differentiation. Of 1 meter cubed, so it's volume divided by day, and therefore it's dV dt. The vessel has a height of 2 meters and a diameter of 2. So this radius is 1, and this height is 2. Great. It says when the vessel is 1/8 full, so it's 1/8 full, find the rate at which the water is rising. So first of all, you have that it's 1/8 full. So what's the volume of a cone? So remember, this little cone here is in the same shape as the one up there. Okay, so the volume of a cone is 1/3 pi r squared h, which in this case is r is 1 and h is 2, so it's just equal to 2 pi over 3. So it's 1/8 full, which means the volume is simply equal to an eighth of this, which is going to be pi over 12. Now remember, the radius is always going to be half of the height. All right. So what I can do is I can say, okay, so the height is always equal to 2r. So the volume of this little cone is always going to be 1/3 pi r squared times h, which is 2r. So it's always going to be 2/3 pi r cubed. So that's the volume. It's always going to be this. Okay, so that's another thing to remember, that in this thing, it's r and then 2r. Why? Because the cone, so again, it's basically similar triangles that you would have done in your junior cert. Similar triangles, so therefore I can say that if this is 1 and this is 2, then it's double, and therefore it'll be double here as well. Okay, so that's that. All right. So remember, the volume, I want to know what is the radius. So the radius, so when the volume is this, what's the radius? Actually, no, sorry, it might. Okay, no, I'm actually going to go a little bit different way of this. Okay, yeah, sorry. Okay, so again, they said that dV dt is 1. Grand. Now what they've asked you for is they've said, what is the rate at which the water is rising? So what is it they want to know? What is the rate at which this is rising? Which is basically dH dt. That's what they want to know. So dH dt, I can say, well, okay, that's going to be dV dt, which is the thing that I know. I need to get rid of the dV, so divide it by dV and multiply it by dH. Because remember, this now would give me dH dt. So I have that dH dt is simply, because dV dt is equal to 1, it's just equal to dH dV. Now, can I figure out? Sorry, that looks really wrong. Is that actually true? Oh yeah, because dV dt is 1. Okay, yeah, okay. So yeah, so dH dV, I can say V is equal to 2/3 pi r cubed. I can say that, well, r is equal to h over 2. So now if I plug that in here, because again, I want to get derivatives with respect to h, so I want h and v in the same formula. So v is going to be 2/3 pi h over 2 cubed. So the volume is going to be pi h cubed over 12. Okay, so now I can calculate dV dH. which is going to be equal to pi h squared over 4. So the 3 comes down, 3 divided by 12 is 1 over 4. That's where this 4 has come from. And basically, now you can say, well, if dv dh is pi h squared over 4, then dh dv is just the flip of it. So it's just equal to 4 over pi h squared. dh dt. Now they asked for it when it's 1/8 full. So that's why I was doing all this before. I was saying, okay, well, I know that the volume is equal to this thing. And the volume is also equal to pi h cubed over 12. Okay? And basically that means that h is 1. So what they're asking is, what is this thing equal to when h is 1? It's equal to, if I plug in h equals 1, I'm simply left with 4 over pi. And remember, it's meters per minute. Okay? So that's it. That was quite a hard one. The next one is just as hard, to be quite honest. It says the rate at which the free surface of the water is increasing. So the free surface is the surface area, which is basically this thing here. So again, what's the surface area? The surface area is simply equal to S, which is going to be equal to pi r squared, or it's, again, because r is equal to h over 2, it's going to be pi h squared over 4. So I want to know what ds dt is. Remember, we have what dh dt is, so I can use that. And I can multiply it by ds dh. Why? Because these two dh's would cancel and I'd be left with ds dt. So, dh dt, we just figured out, was 4 over pi. ds dh is simply going to be pi h over 2. And I want to know this when h is equal to 1. If h is equal to 1, I'm simply left with 2. So the rate of change of surface area is going to be 2 meters squared per minute. Okay? And that's it. That's the last thing to do with differential calculus. Okay? So the very next thing to do is to do integration. Okay? And then that'll be, as I'm sure some of you will be very glad to hear, the very last video of paper 1. So it is just probably another 40-50 hour long video, and then that will be that for paper 1 anyways, and then we moving on to paper 2. Okay, so thank you so much for paying attention. I really appreciate it, and I suppose I'll talk to you in the next video. Thanks.